Good. So welcome everybody to the IMC seminar today. I'm really happy to introduce Jasper van Doornmalen. I hope I didn't do a terrible job of explaining the saying your last name. So Jasper is currently a postdoc here at IMC. And he's also working part-time in a company called Alicanto related to his research topic, which is mathematical programming. So Jasper did his PhD in Eindhoven University under the supervision of Christopher Koenig, which I think is actually correct. And he did some very nice work on algorithms for handling symmetries in optimization problems with discrete variables like integer programming. It has very nice results in that area, and it's not just to mention, this is not just theoretical research. He has also worked in implementing some of these methods in a solver for integer programming called skip. That will maybe mention a little bit about that, I don't know. But thanks a lot, Jasper, for being here.
Okay, thank you, Jose, for the introduction. So indeed, this presentation is going to be about more or less what I did during my PhD. We will start with an example of, so it's all about mathematical programming and how to solve mathematical programs more efficiently by exploiting symmetry structure. Presentation will start with a small example of a mathematical program and how to solve this. And you can actually see that the symmetry there is causing some problems if you would like to solve it in a computational way. Then we turn to the symmetry handling methods that are common, that are more or less traditional, that many people are using. And then we will step to the paper that I did together with my PhD advisor Christopher on the unified framework for symmetry handling, which actually shows that many of these traditionally known methods are actually all fit in this framework, and therefore that they can be combined under certain conditions that also allows for some generalizations. And that's the last bit of the presentation. So let's get started with a small and simple example of a mathematical program that contains symmetries. It's the noise quotient problem introduced by Spralli and Smith. And the idea is that we have a certain number of machines, and these machines need to be operated by some workers. We have m noisy machines and we have n workers. The workers work no more than 8 hours in a day, and the machines need to be operated a certain number of times, di. If they are being operated, that will take a certain amount of time. And if they are operated, then the worker is getting exerted to a certain amount of noise. And we would like to find a worker schedule so that the worker that is worst off in terms of the noise, that worker receives the lowest amount of noise possible. So how can we formulate this? We can create an integer program, choose decision variables xij, which decides how many tasks of type on machine I are being operated by worker j. And the objective is then we want to minimize the amount of noise that the worker gets that is worst off. So we want to minimize the maximum of the workers of the sum for every machine of the amount of noise that you get multiplied by the number of times that you operate the machine. And then we have two classes of constraints. The first constraint says the total time. So if the total time of the tasks that the worker is assigned to cannot be higher than the time horizon, cannot be higher than the number of hours in a day, and all tasks need to be executed. And we have that the variables, they have to be non-negative integer variables. So I suppose that most of you are known to how integer programs are commonly being solved. You make use of, typically make use of breaks and bounds, and you choose a relaxation of this program by dropping the integrality conditions. And you do that in the root node, you drop the integrality conditions, solve the problem using linear programming techniques, and then you do a branching step if the solution that you get is not an integer solution. So in the root node, we consider the problem without any restrictions, or actually the problem that we considered without the integrality conditions. We may find a solution using linear programming. This solution may not be an integral solution. What we do, we pick a variable, it's called variable branching, to say what happens if the variable that we pick. So for instance, we pick this variable, what happens if the variable is 0, or what happens if the variable is larger or equal to 1. By iterating this, by continuing doing this, you get a tree structure, and you can stop at a subproblem if you find an integral solution in that subproblem, which is optimal, or when you can prove that all solutions in that subproblem are not going to be the optimal solution. Now we are in the noise dosage problem example, and the important thing in this model is that the workers here, for the sake of the model, these workers are identical, which means that if I have a worker schedule like this, where now the variables xij are arranged in a matrix like this, in a n by w matrix. If we have a worker schedule like this, I can take the jobs assigned to the first worker and the second worker, and I can swap them. This will give me a symmetrically equivalent solution. And this is what we call a symmetry. And if we look at a branch boundary for the problem of the noise dosage problem, if we can swap these columns, they can actually see that there are two subproblems here in this branch boundary that are actually considering the same feasible region up to symmetry. Namely, here on the left, we have an equal 0, larger than equal 1, and the rest of these are the same. If I flip these two columns, then we have exactly what's written here. And if we do not exploit the symmetries, then if there would be an optimal solution contained within this feasible region here, if you cannot find it, you need to apply a lot of work in order to narrow down that optimal solution is there. And you also have to do the same here because there could be another optimal solution there. But okay, and now the goal of symmetry handling is can we use the knowledge that we have of symmetry so that problems like these are being avoided? Can I reduce the amount of work applied in this branch boundary process by exploiting the presence of symmetries in the problem? So the type of symmetries that we have observed here, they are a well-known type of symmetries. We call them orbitopal. And orbitopal type symmetries are like that you can take variables of the problem or some variables of the problem and arrange them in a matrix like this. And if the symmetries of the problem correspond to permutations of the column set of the matrix, then we call those orbitopal symmetries. So there are various ways to handle orbitopal symmetries. A very common way is to add an additional constraint to the problem, saying that the first column that we have is lexicographically larger than the second, lexicographically larger than the third, and so forth. And this enforces an ordering in our solution vector. And it will turn out that there is exactly one solution matrix here that respects these constraints. Because if we pick two columns and we flip them, if we take a solution that's lexicographically maximal this way, we pick two columns and flip them. If these columns are different, then one of these constraints will be violated.
So basically modeling out. Right?
Yes, exactly. So this is a very common approach to add a constraint like this. And there is a problem with this because this is a lexicographic order constraint. It's not a linear constraint. So if you want to embed it in linear programming solvers that underlie the mathematical programming, you need to linearize these constraints. You can do that, for instance, by fundamental domain inequalities, as Shirali and Smith did in their research. And in a more generic way, you can consider the fundamental domain inequalities as given by Friedman. And another approach is to ignore these constraints in the actual solving of the subproblems, but to apply propagation techniques, which means that we use the knowledge of these constraints to tighten the variable domains even further and reduce the size of the feasible region in subproblems that way. I will come back to this, what this exactly is, but orbitopal fixing, it's a common method. It found its way in many mixed engine programming solvers. And what we showed is, Bertotti has shown that this is possible for binary variable domains. And in our work, the paper that I wrote together with Christopher, the unified framework for symmetry handling, there we show that it can be done for arbitrary variable domains. So that symmetries can be handled on arbitrary integer variables. For instance, in the setting of the noise dosage problem, which was a non-binary problem because the variables xij, there were non-negative integer variables in the binary. So we have now looked at the example of the noise dosage problem with these orbitopal symmetries, but you may ask, what are other classes of symmetries? And that is what I'm going to talk about next. So in this presentation, or actually in the paper that we wrote, we do not really care a lot about what the underlying mathematical programming structure is. We do not assume that we are dealing with binary programs. You can be dealing with arbitrary nonlinear optimization problems or whatever. So the optimization problems are written in the following way. We have some objective function f, which takes our input space, which is typically like the r-dimensional real vector space. And this function is mapped to a real number. And we have some feasible region, which is a subset of the universe. The goal is to minimize our objective, choose a solution from the feasible region that minimizes our objective. The most common way, I would say, to write down a mathematical problem.
And omega here is a subset of what? Is it
So-
discrete? Is it the?
It can be anything. So if I think about mathematical like NIPs, then typically omega is like the Rn, like the real vector space. But you can also think of it can be the binary hypercube or something like that.
I see.
But for the sake of symmetry handling, the results that we found are independent on what kind of problem we have. But it will require you to handle some sort of constraints, and that may impose restrictions on the type of problems that you can do. So using this definition, what is a symmetry? A symmetry is basically a bijective map, mapping from the solution space to the solution space. And we say that it is a symmetry if it preserves the objective of the optimization problem, and it preserves the feasibility, meaning that for any solution, whether it's feasible or not, the objective is preserved and also the feasibility. And okay, this is an even earlier situation. So if we were infeasible, then we will be infeasible again in the symmetric image. And these definitions, this definition of symmetry actually shows that if we consider all the symmetries of a problem, that this defines a group. So the set of all symmetries of a optimization problem, that's a group. Identity is contained. We have a symmetry like this. Also, the inverse works because it's a bijective map, and compositional functions also. So, what are examples of symmetries? Well, we have seen in the introduction the noise dosage problem, where we could permute the workers, or more generically, the index set of the columns of this orbitope. And we can write down the symmetry as follows. Let delta be a permutation of the worker set. We can say that gamma of delta is basically taking our solutions xij and permute the column collections. An example of a symmetry. Another example of a symmetry is, for instance, the stable set problem. So that's given a graph, find the maximum number of vertices you can select that are non-adjacent. If you look at the graph G, which is here the cycle graph C7, then an example of a maximal stable set is 1, 3, and 5. And if I have an automorphism of this graph, for instance, a rotation or a reflection, then what we can do is, for instance, we pick this gamma here, which maps the index to one index higher. Then we can apply the symmetry on the set, and indeed, it is still a set of cardinality 3, and it is again a stable set. So automorphisms of the graph, they are symmetries in the same set. And the two examples that I gave, they are of a discrete optimization problem, but we can also consider symmetries in nonlinear problems. For instance, this kissing number problem here, we have a sphere of unit radius around the origin, and the question is, are we able to fit 6 spheres that touch this sphere around the origin, also of unit radius, such that these 6 spheres are non-overlapping, or at least they can overlap in the boundary, they do not overlap when we consider the integrals. You can write this down as a nonlinear program. We have we introduce vectors xi. Let's say this is the vector specifying what the center point of these outer spheres is going to be. The center point, because these spheres must touch the sphere here on the inside, the distance to the origin must be 2. That's what this constraint says. And they must be non-overlapping, which means that this constraint must hold. If we take the distance between these two, then it must be at least 2 as well. The type of symmetries that we have here, we have the subsymmetries that are orbitopal, because what we can do is take 2 of these indices I and j, and basically swap out the coordinates of these 2. So that's orbitopal symmetry. But we also have the geometric symmetries applied to this problem. If I take a rotation or a reflection around the origin, then I can rotate the whole bit, all the coordinates of these outer spheres, and that's again a symmetry. And note this is this type of symmetries, they are geometric, they are not discrete. They are not discrete in a way. Actually, this provides an infinitely large symmetry. So now we take a step back to the literature. So in the literature, they did commonly not consider symmetry groups that are this generic. Very often they consider this type of symmetries where we have a solution vector and we apply a solution, a permutation of the index space of the solution vector, which basically means that we take a vector, we flip some entries apart. Various authors have studied this type of symmetries, and also there has been some work in reflection symmetries. For instance, Christoph has recently posted a paper on the archive that deals with reflection symmetries. And you can also think of rotational symmetries and many more types. So, okay, and one last thing. Again, I would like to stress that the goal is eventually that we want to reduce the size of the branch and boundary by exploiting the symmetry argument. Here we have the example of finding an optimal puzzle piece. So we start with a puzzle piece where all of the sides still have to be decided. And by branching, we narrow down towards what the puzzle pieces actually are. And we can recognize that this puzzle piece here, if you can rotate it a bit, then you get exactly this. And this is the type of settings that we want to avoid. So what are the traditional methods for symmetry handling before we jump to the results of our paper? I would like to highlight two methods. One is a more dynamic symmetry handling method, and another is a more static symmetry handling method. And what I mean with that is a dynamic symmetry handling method is a bit adaptive to the actual solving procedure, that's to the branch and boundary process. And a static symmetry handling method that's a bit like what we've seen before, where I say, look, these are the constraints, and these constraints eliminate the symmetries from the problem, and these constraints are going to be enforced by the branch and boundary process. What happens in the literature is very often they are considering binary programs, or at least where the symmetries operate on the binary variables of within an optimization problem. And also they consider the settings where the symmetries are exactly the permutations of the solution vector. I would like to stress, I picked out these two methods, but this is not a complete overview of what's floating around in the literature. You also have orbital branchings via sim-stable cuts, which are actually also symmetry handling constraints. And you can also think of core point methods, and there are many other classes of symmetry handling methods known in literature and that are being used in practice as well. But we focus on these two for the sake of this presentation. So first, what is isomorphism pruning? This is a dynamic type symmetry handling method. The idea is that if we can recognize that we will find symmetrically equivalent solutions elsewhere in the tree, then we can stop searching within the branch and boundary node that we are in and just say, oh, somewhere else in the tree you will find a solution like that. Question is, how can you do that in a systematic way? And Margot introduced this for a rather static branch and boundary, and later Ostrovsky showed that this can be done for arbitrary branching processes. And his rule that he came up with is the following. We are in a binary setting here. So that means that if we make a variable branching decision, that a variable gets branched to 0 or to 1. And what Ostrovsky did is basically he chooses the variable that you branch on first. He gives that label 1, and the variable that you branch on next gives it label 2, and so forth. And then he looks at a branch and boundary node. He says, what are the labels that are fixed to 1 by branching? In this case, that's only this guy. And is there a symmetry that turns these labels into labels that are setwise lexicographically small? So what that would mean, this is the first branching step, that's the second branching step. If this corresponds to a 1 fixing, then the set of 1 fixings in this node consists of 1 element, namely label 2. But I can rotate this puzzle piece by 1 turn, and then the element 2 gets mapped to 1, and the set 1 is lexicographically smaller than set 2. And that means that his rule is being satisfied, and we can cut off this branch and boundary. And you can actually see it. This partial puzzle piece, it also lives over there. Therefore, yeah, we are allowed to do that. In principle, the representative element that he chooses is the element where the set of one fixed variables is lexicographically minimal. So if you are lexicographically non-minimal, then we are perfectly fine to kill that branching boundary.
So this only works for this type of permutation, like symmetries. Because
He defined it like that, yes. And
I'm just
actually,
thinking that sometimes this lexicographic thing, it mods out the symmetry, as I
Mhm.
said before. But I don't know if it always mods out any symmetry. I'm thinking of a more arbitrary symmetry group. And then that lexicographic maybe it's not modding it out, so I see it working in this setting.
I think the answer is yes. But the reason that I think that is because of our result of our paper that generalizes all of this. I showed but in this setting, so you may think that the fact that the binary problems are included and that it's specifically the one fixed entries, but that makes a difference.
I'm just thinking of the way that the fact that he's using this lexicographic
Mhm.
order to.
But then the lexicographic order you can use for any vector.
You can what, sorry?
For any vectors, you can still order by lexicographic. You don't need.
Yes, but I think that the lexicographic order is referring to only this permutation, like symmetries, as in it mods out those types.
Yes.
Specific.
Yeah, we are.
Whereas if I have another group action, which I'm thinking, because I have problems where I have another group action, that's why I'm thinking about it. So that's not the.
Well, but
that was
in binary problems, the thing is, if you have anything else, it turns your binary solution vector possibly in something that's not binary. So it must be a type of group that takes 0, 1 vectors and maps it to 0, 1 vectors.
I guess that you're asking about all like kind of arbitrary.
Yeah, okay, anyway.
Okay.
I won't interrupt more, yeah, I'm sorry.
Okay, so where was I? Okay, so this node can be effectively, we can just get rid of that node because of this isomorphism pruning. What's nice about isomorphism pruning is that it can also be combined with other symmetry handling methods. One is orbital fixing. I will not go into the details. The other class of symmetry handling methods is static symmetry handling constraints, and these typically make use of a lexicographic order. So we have the solution vector, and we compare solution vectors with symmetrically equivalent solution vectors. So what's the lexicographic order? Basically, we compare two vectors, and the first entry where these two vectors differ determines whether what the lexicographic order is. In this case, this vector here is lexicographically larger than this one, because the very first entry where they differ is larger here than that it's just there. So how can we use this? Lexicographic order defines a total ordering of the real vector space. So what we can do is, in fact, we can enforce this constraint over here, which says that if we have our symmetry group, we can look at the orbit. This is just a set of all symmetrically equivalent solutions. And we are interested in that solution that is the lexicographically maximal element in there, which means that we kill all of the symmetric. There's exactly one solution that survives this constraint within each symmetry group.
I see.
Enforcing this can be difficult because enforcing this can be difficult, but the thing is, how can you handle such a constraint? Because very often we are in a mathematical mixed into linear programming case, and again, this is not a linear constraint, this is lexicographic order. So what can you do? You can think of separation, like separation oracles, but you can also add linear constraints like fundamental domain inequalities or semi-stable cuts. But I will focus on propagation, actually variable bound propagation. So what's the idea of variable bound propagation? Here's a more or less technical overview of what it is. But at a certain branch and boundary node, for each variable that we have given a certain domain. For instance, it can be 0, it can be 1, it's fixed to 0, it's fixed to 1, or something in between, or something in between. And at the branch and boundary node, we are given all these domains for all of the variables. And then what you can check is, instead of doing anything with this constraint in the actual underlying LP solver, we can look if we can find some inference of the variable domains. For instance, if we are given these fixings and we are given this constraint, is it possible that if this constraint is satisfied with these fixings, that we can find another fix? And we call propagation complete if subject to a constraint or subject to a set of constraints, all fixings can be determined. So here's a simple example. We have a vector x1, x2, x3, and we compare it with x4, x5, x6. If so we have a binary 6-dimensional solution vector. We have some fixings that are given. We can basically fill in these fixings here in this constraint, and we can check this constraint. Now, given these initial bounds, we can see that there's no way that this constraint holds if x4 is equal to 1, because then constraint is violated, which means that we can safely set x4 to 0, which is a propagation set. And we can continue checking this, but in the second row, we see that x2 is equal to 1 and x5 is equal to 0, which means that no matter what the remaining variable entries are set to, we will always satisfy this constraint, and therefore we found the complete set of variable domain reductions with respect to this constraint. In this example, this constraint is exactly one constraint that's given, but you can also think that this set C is basically the intersection of various constraints. And in that case, complete propagation is a very interesting question. Are we able to find all the possible fixings that we can find? So the idea is that we use propagation techniques to enforce this. And if you look at this example and appropriately label the entries like this, then you will find that the branch and boundary becomes significantly smaller. If we do this one fixing here, actually all the rotations enforce that all the other entries can be fixed to 1, but over here we find a lot of fixing. So you can see by enforcing this constraint, we are able to reduce the size of the branch and boundary, which is good. So I've mentioned effectively two classes of symmetry handling method. On the one hand, we have dynamic methods. On the other hand, we have static methods. The dynamic methods are nice because they are adaptive to the branching decisions that you make. You don't want to start with a symmetry handling constraint, which turns out to be really weak in the first few decisions of the branch and boundary that you make, because then you start duplicating a lot of work. By pulling that work forward, by adapting to the actual structure of the branch and boundary, you can typically, or it's more of a feeling that this is a more a method that you actually want to use. Unfortunately, both in this dynamic case, isomorphism pruning and symmetry handling constraints of this type, testing the isomorphism pruning rule is NP-complete, and a complete propagation of this constraint here for all of these, that is a co-NP hard problem. There are some compromises possible. You can test weaker variants of the isomorphism pruning rule. You can decide to choose an appropriate subgroup, which is sufficiently large, and do some reductions with that. But actually, complete propagation and testing the isomorphism pruning rule for Ostrovsky, these are difficult problems. What's nice about static symmetry handling methods, there are common special cases. For instance, the orbital example that I gave all the way at the beginning. This is a type of symmetries that can be efficiently handled with propagation, as has been shown by the binary case. And what's also said is that these two methods, it's not very surprising that they are not compatible, but what we would like to do is use the ideas of both worlds to combine certain things. And I would like to add a little aspect here, namely the orbital fixing that Benoît introduced. We did actually show a slight dynamification of that you can choose this constraint in a more dynamic way throughout the branch boundary search. So I would just like to mention that. And on this note, that's actually something that inspired us to do the following work. So I would like to talk about the unified framework for symmetry handling, which is a paper that I have together with Christopher. Basically, what we are going to show is these methods that we have seen, these traditional methods that were binary variables, and they are actually part of the family of symmetry handling methods. And that allows us to combine symmetry handling method, that allows us to use the symmetry handling methods in a more generic context. So what is the starting point of our contribution? Basically, we started looking at these static symmetry handling constraints. And what we wanted to do is dynamify these symmetry handling constraints. So instead of looking at these, we invented a map sigma that is for every branch and boundary we choose a map. Effectively, we are morphing the lexicographic order that we are here for every branch of boundary node beta. if we have if we are able to choose the sigma arbitrarily for every branch boundary node, then it's very likely that we are just removing symmetries from the problem. So there are some conditions that the map sigma has to comply to. So I will explain what these conditions are and that these are symmetry. So how do we choose the map sigma beta? Basically, we use sigma beta as shorthand notation for this guy here. We take our solution vector x. What we do is we apply phi beta to it, which is a bijection. So we morph our solution vector by applying a symmetry. Then we apply a permutation, which shuffles around the entries, and we then shrink the vector to the first m beta elements, which reduces the vector size. And by doing that, we actually also turn this into something that, whereas here we removed all the symmetries, by shrinking the size, we now allow for some room in choosing these things. So what are the conditions that we have? I will read out the main result. So assume that we have a branch and boundary that enforces this symmetry handling constraint over here and proves it in feasibility only, and that is more a technical assumption, so that we actually know that this technical assumption for the following sentence. For any solution that we have, any feasible solution, there is exactly one leaf of the branch and boundary, or array in that sense, where a symmetric solution is feasible if these four conditions fit. In the next 4 slides, I will quickly go over these 4 conditions. So what this constraint says, if our sigma beta is chosen in a very specific way, then these are symmetry handling constraints that we can apply. So if every branch and boundary node, I can enforce this symmetry handling constraint. So what is condition 1? We are in the branch and boundary node, and the idea of condition 1 is that you inherit certain symmetry structure from your parent. So if this is only on pi and m, so if at the branch and boundary node alpha, we have that pi alpha of x looks like this, then the first m alpha elements, so these were the ones that we were looking at, they must be the same set for the child beta. In other words, the child beta, it grows the vector that we allocate. And the guys here, that is some free choice that modeler can choose. Second condition, if beta has a sibling, then these symmetry pre-handling structures, as we call them, they are the same. That is an easy condition. Third condition, I said that this m parameter, it shrinks our vector, which means that we are not looking at the full vector for the sake of symmetry handling, which means that we are looking through some kind of glasses at a problem. And what this third condition enforces is that if we have a solution that's feasible at node beta, which means it has a feasible solution and that respects the ranging decisions made to beta, and we have a symmetry psi, if looking through these glasses of the sigma function, the solutions look identical, then we know if this guy is feasible at node beta, then also the symmetric counterpart must be feasible. Must be enforced by our choices of the function sigma. And the last condition is that I say it allows us to change the viewpoint. If at the node alpha, we have that the feasible region of node alpha is the same as the feasible region at node alpha after applying permutation, then we are allowed to use, starting at node alpha or starting at node beta actually, we can look at the problem instead of the feasible region at node alpha, we can look at the symmetric counterpart. And this is quite useful for a simple reason. The only difference between this position here, where these two feasible sets are the same, is that we make a branching decision. So we are allowed to move around this branching decision after it has been made for the sake of it. And that turns out to be quite a useful approach. So
Go back to the condition 2.
Condition 2, yes.
Siblings have the same. What was the sibling?
The sibling is, if we have a branch and boundary, then we at this node we choose a variable, or actually we don't assume variable branching. We split this feasible region in 2 parts. And beta and beta prime, they are called siblings. They are at the same level of the branch and boundary, and they are similar. Okay, and then you must choose them in the system. So actually, the decision that you make before walking out of alpha, that has to be, at that point, you have to make the decision, not when this node is being used. Thank you. Okay. Any further questions? No. Okay. So there are lots of consequences of this theorem because it's stated in a very generic way, which means a lot of things. First of all, we do not make any assumption on the variable domain spaces, whereas many symmetry handling methods before were on binary variable domain spaces. We can now do it suddenly on arbitrary variable domain spaces. So it's applicable to non-binary optimization problems, and that's actually what we also did in our computational experiments. Also, we have a weaker assumption on permutation groups. So in my introduction, I was looking at symmetries, which are arbitrary groups of bijective functions that are objective and feasibility preserving. But traditionally, people were only looking at this subset of these symmetries, which are the symmetries that morph around the solution vector entries. And in our framework, we do not have any such assumption. We just have that we can look at arbitrary symmetry groups. So if you can handle this guy for arbitrary symmetry groups, then you have found a symmetry handling method. At last, this framework, so we have to choose these sigmas in a very specific way, but it turns out all of the methods that we have seen up to this point in the presentation, they fit in this framework by again an appropriate choice. So that static symmetry handling constraints, orbital fixing, and isomorphism proving. Orbital fixing is given by Vendotti, even his dynamification, and even his dynamification, and I forgot what I wanted to say there. But and the last thing is, if we have two methods that were deemed to be different symmetry handling methods, and it turns out that their sigmas are the same, then they are handling the same set of symmetry reductions, and they can be applied at the same time. And this is quite useful because it also allows us to take a static symmetry handling method and turn it into a dynamic symmetry handling method that can be used in conjunction with an existing dynamic symmetry handling method. Just by saying, we take the dynamic symmetry handling method, we look at the choice of the sigmas that they do, and we apply that now to the static symmetry handling. So we did some computational results. We have implemented our methods in Skip, or actually we have chosen a few symmetry handling methods. We generalized them for arbitrary.
Just a question. So in your result, it all boils down to having this sigma, right?
Yes.
You assume you have to be clever to find the sigma at the very beginning, or does it given by the problem, or in practice? I'm thinking practice.
So in practice, you choose a procedure on how the sigma is constructed. So what you can do, for instance, you can start with an empty sigma, and when you make a branching decision, then you must ensure that the choices that you make actually enforce that these conditions are being preserved. And a very easy one is, for instance, if you make a branching decision, you pick the variable that you branch on, and you put that variable next in the solution variable. So then you grow. So that's how you do it.
Okay.
What's that?
So I don't know if I'm making a well-posed question, but anyhow, like how general is this actually? Like, can you show, or do you have any like chance of showing that any possible like symmetry handling technique can be captured by this, right?
Okay. So this basically boils down to the question we have. We assume that we are dealing with the lexicographical. How? So what happens if we substitute it for another order, which may or may not be a total ordering? Can we cast the sigmas in such a way that we also support these orders? I don't know.
I mean, orders. I mean, lexicographic order is pretty general, right? In the sense that by like taking
any total ordering, yes.
And yeah, any total order, right? Any order that comes from a cone, essentially, yes, you can capture it with a.
Yeah, but
so it would need to have something like very non-conic in order.
Yeah, and also in the way that I phrased it. So this is the property that I have, the framework. We say that this bijection must be a symmetry, which means that we are not free to choose our solution vector X however we want. It must be a symmetry. But I think we can start with any morphing of the solution vector and then start using the symmetries after that. I'm not sure about that. I'm not sure. So does that answer your question? More or less. Great. So we did some computational experiments. We have implemented our methods in SCIP, which is a constraint instance programming solver, which already did have some symmetry handling methods, had orbital fixing implemented, orbital fixing, and Symmetries export, which is effectively handling one lexicographic order constraint. And what we did is we generalized these, that they also work for non-binary variables, and also dynamified some of these constraints. So so this is software. We use SCIP, we use SOAPLEX as underlying MP solver, and we use BLISS, which is an automorphism detecting program, and that is being used. We feed the problems with our IP formulation or constraint into the programming formulation. This detects the symmetries of the problem that are induced by the formulation. We look at the instances. So there's a benchmark test set, MIPLIP, MIPLIP 2010 and MIPLIP 2017. There are 126 instances that show this symmetry structure. We picked those instances. We looked at the noise dosage problem instances, both the instances from Charla and Smith from 2002, but these were rather straightforward instances, and we extended them to larger problem sizes. We looked at covering design problems, which is yet another non-binary, non-orthogonal type of symmetry problem with non-binary and no orthogonal symmetries, and we have time limit of 1 hour. Our settings are the following. We compare to the traditional method of SCIP, which was orthogonal fixing. We generalized it to a non-binary symmetry handling method. So the word fixing turns into reduction, because variable domain reduction can be anything now. Same with orbital fixing. And we implemented lexicographic reduction, which effectively takes one of these x lexicographically larger equal to gamma x for one symmetry gamma. These are the settings that we are looking at. So we compute the symmetry group. This gives us back the direct product of various components of the symmetry group. We iterate over each component. If that component turns out to be orbitopal, meaning permutations of the columns, for a certain choice of the matrix, then we use dynamic orbitopal fixing or dynamic orbitopal reduction. And if it doesn't, then we make use of orbital fixing. And on top of that, we can choose to whatever which sigmas are used by this orbitopal fixing, we can handle this constraint in addition to that for a subset of the permutations. Results, they look quite good. So in the traditional SCIP setting, the best running time was 728.88 seconds. We were able to reduce that to 691.22 seconds, which is an improvement of 5.1%. Fortunately, there was one instance fewer that we were able to solve, which is a very large instance. And if you look at the solved instances, then we win 4.9%. You can also see the combined effect of using compatible symmetry handling methods here, because if we just use orbitopal reduction or just use lexicographic reduction, then we see that the times that we report here are actually higher than the combined effect, which means that actually investing time in running an additional symmetry handling procedure, that can save time in total for the total benchmark research. We also looked at Charla and Smith. This is a non-binary problem, which means that the standard SCIP methods are not able to handle these symmetries because they were only implemented for binary problems. We also compared to Charla and Smith's method, which adds numerically unstable cuts to the problem, and that caused that there were many instances that claimed an optimal that claimed that certain solutions were optimal, whereas when we ran the same model, that we found even better optimal values, which means that the introduction of numerically unstable linear constraints, that led to that the guarantee of this optimality was basically lost. So
so your solutions were better, or was it that it was just you're saying that the first LP had basically wasn't numerically stable? That's what I'm understanding.
Yes, they had constraints, linear constraints that have a very there's some. So the constraints are of the type 2 to the k. So it's basically mocking this correct order constraint with a linear constraint. And this causes that there are coefficients which are really small and coefficients which are really big.
This makes it look.
Yes. And yeah, if you start solving it, then it will decide that certain solutions are infeasible, while there is still an infeasible solution contained there within. That's causing a problem. So yes, they were faster, but yes, they also gave the wrong result. So there's not really something that we can compare.
And then no symmetry handling does give the optimal solution.
Yes, that's great. See you. And we also compare to a set of non-binary and non-orbitopal symmetries. So the noise dosing problems that were orbitopal, these are not orbitopal. And for that in SCIP there is no symmetry handling method. And it turns out we win 81% compared to no symmetry handling. We are effectively comparing to a very symmetric instance with no symmetry handling, so that's a bit unfair, but it conveys the combined effect. So to summarize this presentation, I introduced mathematical programming, what symmetry in mathematical programming does computationally in the branch boundaries. I talked a little bit about traditional methods and showed that many of these traditional methods fit in our unified framework for symmetry handling. We are able to combine we are able to generalize existing methods and combine various symmetry handling methods to get a better joint effect. We report a 5.1% improvement over the best existing implementations compared to no symmetry handling up to 83.1%. And on that note, I'd like to wrap this presentation. Thank you all for listening.
Thank you.
Please go ahead.
Out of curiosity, have you come up with a problem, real or made up, in which the technique of branch unbound would virtually never come up with the optimal solution, but with exploding symmetries would?
You mean that? Yeah, so you ask, are you aware of a problem that has these symmetries, that if you do not apply symmetry handling, that it's not able to find a solution? In theory, the answer is no, because for discrete problems, you can always spend finite time and find the optimal solution by a sufficiently large branch and boundary. This branch and boundary may, however, not fit in your machine. I am aware of a application that's really interesting, which is the placement of windmills on a. This was the Danish energy company. They had a field on the North Sea, and they wanted to place the windmills in a certain way. They made a MIP, and these windmills, they were basically wind turbines. They were basically, you could interchange their positions, so they had orbitopal symmetries. This was work before, it was like 2008 or 2010. This orbitopal fixing didn't exist at that time yet. And they spent a lot of time solving that problem on the national supercomputers. And in the end, they just chose a solution. And now you can take that instance and run it and actually solve it within a few minutes on your laptop. So that shows that using the presence of symmetries is actually helpful for solving problems.
Yeah, in my personal computations, I have massive polynomials, and the size of the problem grows a lot with the number of variables or the degree, to the point that it doesn't fit in the computer. There's not enough RAM. But if you do the symmetry reduction, then you can run it. But as you said, in theory, it should be able to solve it, but it's just that in practice, the computers are not big enough maybe to handle the non-symmetric case. And whereas if you mod out the symmetry, then you reduce the size of the place and variables, etc.
Was your RAM consumption then? But it is either timed.
I didn't run the instance, but I know that they reran the instance on a newer version of Garobi. I thought it was another old version like Garobi 7 or 8 that did introduce these orbital reductions, and they were able to do it on that.
Okay.
have a question. So, you mentioned some percentages in savings. Compared to whatever, the best method and no symmetry kind of,
Yes.
right?
Mhm.
Sometimes, there are lots of problems where when you scale them up, this actually, the savings are non-linear. So actually that 5% can become 50%, right?
Yes, yes.
A lot more. Do you have any comments on that regard? Like,
Yeah.
are there like benchmark problems are bigger so that you can like
Yes,
claim
that's-
better results?
okay,
It's
that's-
just because of the non-linearity.
So that's a bit of a problem with the testing method because how do you deal with instances that time out? So we use the 1 hour time limit. You can actually see here, I think it's the covering design problem. So these are parameterized in VK and MATLAB. Use larger parameters, then the problem will also be larger. Or I think the K needs to be like half V, and then you have the largest possible instance. But if we generate more instances, then this no symmetry handling will just reach the time limit. So then we have no idea what the time gains are, and then this is the only column that we can look at. And actually here you see it. So if you would look at the list, we will see that the combined methods, or actually the methods they use in handling, they are able to solve a lot more instances. And the no symmetry handling stops at a certain time. Like this is just the time limit. Then the question is, what is the time limit that you are counting? You say it's twice the time limit, then you are giving them, then you are saying that they are worse than they actually are because they may solve like 1 minute later. So we chose if it reaches the time limit, then in this column we report it as if the time limit was the time that it's required to solve the alternate.
What about when you compare the best available one, where you were saying 5%?
Like over here. So there are also some instances that were able to be solved. So there are 126 instances in total. And you see that only half of these can be solved. Many of these are just instances that are too difficult, so they can be solved if you set a record, but they set a time limit to 3 hours or something. That's a massive amount of RAM. So there are like 60, 70 instances that can be reasonably solved within 1 hour. Yeah. So it's, the design of experiments is always a bit iffy. Like,
Yeah, it's just
it's
like a benchmarking
Yes.
thing, like when you claim 5%, someone might complain, oh, it's only 5%, right? But some problems when you scale them out, actually, it's not 5%.
Oh yeah,
more.
but these are
It's much
benchmark,
better. So
these are benchmark instances, so they cannot be, we can like duplicate them, but they are not parameterized.
Okay.
But yes, for the covering design, yes, you can, these are parameterized, you can still get even better numbers. But then the question is, what are you going to do with finite?
Okay, fair enough. Any other questions?
Anyone online maybe? I don't know. Please.
I have a comment. I feel that it's missing the amount of resources, computational resources you are saving. I mean,
You mean in time?
memory, maybe.
Yes, there were some memory timelines. I remember there were a few instances in MATLAB that timed out because of memory, because these were very big to start with, but I don't have the numbers present. I think in the paper we reported there's like 2 instances that fail because of memory consumption. But I don't have the numbers present here.
Thank you.